I will start with my talk on Make Your Project Solid. My name is Benjamin, and on Twitter I'm the Eberlei, and I come from Germany. And I'm very happy to be here, and I'm hoping that you enjoy the talk. If you have any questions in between, just ask them, and then we can sort of discuss them, or we can do it at the end. Okay, so I work at a company called Coifu, and we do projects or help people create high-quality websites. And I'm also working on the Doctrine ORM project as a lead developer and contributor to the Symphony project. And yeah, you already saw the Twitter name. So when we talk about making projects solid, then we have to first ask the question is, why do we want to write object-oriented code? And who of you is writing object-oriented PHP? Yeah, so quite someone who's writing more like procedural or function-based PHP code. Some people, okay. So essentially, then yes, the solid. What we'll talk about, the solid principles, do not apply to object-oriented code exclusively. They actually also apply to all the other different paradigms of programming, and they have just been known to come from the object-oriented world. So what makes object-oriented code, why is object-oriented code nice? We can manage complexity with it in a simpler way than when we have procedural code. And it allows us to write more reusable code than in the procedural paradigms, and more maintainable code. So this is sort of the claims that people say what is actually object-oriented code has as benefits over procedural code. But just seeing these benefits doesn't really make us understand how this happens. How does object-oriented code actually allow us to manage complexity, reusable code, maintainable code? Actually, when we start out writing object-oriented code, it sort of looks very procedural at the beginning. So you have like objects, and there's classes, and they have names and whatever, but this doesn't really make the code object-oriented. It can stay quite procedural. So how do we reach this state where we have like object-oriented code? So the solid principles are actually 5 principles that were written by Robert C. Martin in a book in 2002, and he didn't invent the principles himself, but they have been known for quite some time, and he just sort of gave them the name, solid principles, grouped them together, and described what they actually are and how they can help you write better object-oriented code. Some of them actually have scientific background, but most of them are sort of like by people using them, it has actually been seen that they lead to better object-oriented code. So we will do this by example. So I will show a little bit of code. I hope everybody can see it, but I will also describe the different steps. So it's not necessary to understand all the code examples or see them. So as an example, we have a little component that is necessary. It should display the weather of some country, some state, show the wind conditions and all this. And the requirements are that the service that we want to write should be independent of the data source. So we might start with Google Weather, or we switch to something different. And we also have different requirements for this component. I will show how we can use object-oriented or the solid principles to write the code that is very reusable. Okay, the first principle is actually from my opinion, the most important one. It's called the single responsibility principle. And it states that there should never be more than one reason to change a class. So whenever you have a class, it should only be in your system for one reason. And whenever this reason changes for whatever requirements change or anything else, then this class might change. But there should never be a class that has too many responsibilities and changing too much, changing in every use case and all that. And you can see from the principle actually that we apply this in procedural programming already by stating that a function should only do one thing. We're thinking about functions in terms of like it should do one thing, and it should not do like 10 things or 100 things, just one thing. And whenever the thing changes, then the function changes. And so this is applied to object-oriented code. And it also applies to the system level as well. You can also think about system level. I have a component, I have a subsystem in my application, and it should only change if this like big question changes and not when all the other details change. So it's a sort of a very generic principle, not applying to object-oriented code alone, but sort of to everything we do in software development. How does this look like in object-oriented code? So I hope you can see it in the back. I will explain it a little bit. So we have a class here that's doing several different things. We have a function that gives us the weather for a location. So this is what the system is actually supposed to do. We want a class that gives us like the temperature, wind speed, something for some location. And what the function does is it delegates to several other private methods. The first one retrieves the data from somewhere. Then with this data, which is XML in this case, we'll actually start to extract the values that we need from that. So we have a method extract weather, and then we return the weather here. So this looks very simple because the public method here only has 3 lines of code. It's like sort of, wow, this is very simple code, I can understand it. But the problem here is that this method does quite some different concerns. So the first thing is we fetch data from a remote location. What do we need for that? Today maybe we need HTTP, but another web service might work over a different sort of like protocol, FTP or whatever we can come up with. And then we assume here that the return value is XML and some specific format, then we pass the specific format. And we also have changes here like converting miles to kilometers, and so there's many different things here. And the problem is the class has to change whenever one of the different responsibilities changes. And this can mean that when the class gets bigger, that the class has to change quite a bit all the time. And this, of course, introduces lots of risks. Whenever you change something, there's a risk that you break it. But also, it reduces the reusability. For example, we could have a really, really nice HTTP client hidden somewhere in the getData method. And we might want to reuse it at some other place. But it's hidden so deep in this method that we can't actually reuse it. So we start like re-implementing it or copying the whole code over to the different place. And at the next day, we have 2 HTTP clients. And then depending on if it's like, again, written and hidden somewhere deeply, then the next use case, we might have another HTTP client implemented in our application. So the single responsibility principle helps us build reusable classes. How do we do this in our case? By composition. So object-oriented code allows us to compose different objects together, which means one object holds a reference to another object and can use all the capabilities of this object. So in this case here, we have, again, the Google Weather Service, and it accepts an HTTP client and a Google Data Parser object in its constructor. So whenever, we're still very specific here, so it's still about HTTP, but if something changes with the HTTP client, we can change the HTTP client exclusively. Also, we can reuse it now. And the parser here, this might change if we use the HTTP client to fetch data from another source, then we need a new parser to parse this new format. And this allows us to exchange the code that is used here without actually changing this big class which handles the interaction. So the single responsibility is about one responsibility per class and separation of concerns. And you should keep in mind that this does not apply to the class level exclusively, but to everything, essentially. One problem is that responsibilities are very hard to detect. If I talk about reusable code, then you might actually don't know what you need tomorrow and what code you actually want to have reusable. And depending on how small the components are that you write, you might actually run into problems naming them or finding out what the different responsibilities in the code are. So it's not really easy to apply this to everything. And the more detailed you get, the more complicated it gets. So this is something that you have to learn by experience. The next principle is the open-closed principle, and it has been known as the most weird one or most harder to understand. And it actually states that any class or function should be open for extension but closed for modification. Which sounds very technical, and we don't really know what it means, like sort of just by reading this. I always explain it in a way that we want to prevent having to change all the details of a class if it's not really necessary. That means we don't want to change the class, for example, if a collaborator changes. So in our case, for example, here's an example where I show a switch statement over the different services that we have, like Google Weather, or in Germany we have one called weather.com. And there are probably millions of different services that provide weather data. And what's happening here is that we do a switch statement over the actual implementation of the weather service. So we have a different API for Google and then a different API for the weather.com service, and maybe we have even more different APIs for the for other services. And what the open-close principle wants to prevent is that you have to change code when it's not really necessary. So, given I say to you, you have to implement this new data service now because they are free and their data are much, much better, what do you have to change in your code to get it working? You have to implement the new data client, but then also, and this is the thing that you could have avoided, is you have to go into this class as well and add a new case statement and add more code there. So you have to add this new service here and call this new service and return the data from there. So how would code look like that does not violate the open-close principle? In our case, we just accept a common interface for this weather service, which looks the same for any of the different weather providers. And we ourselves write the code in a way that it is possible to add a new version of the code, extend and modify the code without actually changing all the occurrences that we have there. So we only have this one call, get weather for location, and this interface here requires you to implement this for every new service that you write. So whenever you add a new service, you can just put the new service in the constructor, and you don't have to change this lines of code here anymore. And the open-close principle wants to prevent you to change too much, because changing always entails risk. The risk of breaking something, and obviously this depends on if you automate, or if you have automated tests for your code maybe, then you can easily detect them very fast when you break something in your code. But if you don't have automated tests, for example, then you are often, developers are often, they don't want to change the code because they don't know if the change might introduce some breakage. And they don't, at some point you may not be able to actually test this manually yourself if your change is now breaking something, or it might take much longer to test this for you, like you have to set up the data in specific ways and it takes minutes, hours or something to actually get the system in a state where you can test the change that you made. So changes introduce or might introduce errors, and we want to avoid them as much as possible. And this is what the open-close principle says. We want to write our code in a way where we don't have to change the existing code and only write new code and put it back together in new ways. And this is what object-oriented code allows us to do with references to objects and using interfaces to define abstract concepts and implement them in new ways. Ideally, we want to write code only, and we want to never change it, and only compose all the objects that we have in different ways. This is obviously something that is a very idealistic world that we're never going to reach, but we want to get there as close as possible. The next principle is something that I think this is the one which is scientific, has some scientific papers written about it, the Liskov substitution principle. And it is also stated very generically. Functions that use references to base classes, so a base class is like the interface, for example, or an abstract class, they must use objects that are derived from this base class exactly how the base class defined them. So if you write an interface and in this interface obviously you describe how this interface should be used, then you should never change this in a base class. You should not change the assumptions of the interface in a class that derives from the original one. So let me give you an example. We've seen this before. In our weather component somewhere, we want to convert miles to kilometers. So Google shows the wind speed in miles, for example, but we want to display this in kilometers. So we have a very simple class that just converts miles to kilometers. And the input is a float, and we return another float. We divide this by the factor that we find somewhere to give us the right value. So we get into trouble when we start changing the assumptions of this class. So the distance converter by now takes a float and returns a float. And we could go and change it in a way where it only allows positive values instead of before it allowed both positive and negative values. And also we change it to return a string and also add something like the kilometer at the end. So what we changed here is the assumptions about the input and the output. And when your code now accepts a distance converter as its argument, it might actually need to check if it's a distance converter or if it's a formatting distance converter, because the behavior is different. So, as we have seen in the open-close principle before, let me go back. Here we have the assumption that the interface works the same all the time. Everybody implements the interface correctly. You get a location and you return the weather. And that is basically what I assume about this interface. And if I now go and write an implementation which changes these assumptions, then the code will break, obviously. In statically typed languages, this will be prevented by the compiler. But in dynamic languages like PHP, it's perfectly possible to do this. But this introduces lots of weird debugging problems. So when we are going to use objects and base classes and interfaces, then we should really apply the Liskov substitution principle and don't change the assumptions of the interface in base classes. Always keep the assumptions the same. So the principle says be less, you're allowed to be less strict on input, so you're allowed to accept more data, because this obviously doesn't break code, allowing more. And you can be more strict on the output. For example, if I say to you, this interface only returns floats, then I obviously can return an integer because it's like a float .0 something. So I can be more strict on what is happening. What I'm not allowed to do is to be more strict on the input, because then the user actually has to start deciding if it's the one or the other implementation, because he has to know about his input he's allowed to give to the class. And you're also not allowed to return more than the interface defines, because then the client again has to check, is it a string now that I get returned, or is it still just a float? So by violating this principle, you actually put responsibility on the user of the class to decide what happens. And we want to avoid that. We want to make all the decisions ourselves and have the client only worry about the defined interface. So more is allowed as input and less is allowed as output. But generally, we should not change the assumptions and keep them the same all the time. And this is what is called subtype polymorphism. So this is one kind of inheritance called subtype polymorphism. You have an interface or a base class, and all the implementations of this interface or base class do it in exactly the way that the interface defined. And they don't add more functionality, they add or add a method here, add a method there. They're just used for this specific purpose and just implement the API that the interface requires. The next principle, to check this time, I'm probably much too fast. Yeah, I'm very fast. Okay, the next principle is the dependency inversion principle, and it states that high-level modules, and I'm going to come to the definition of that, should not depend on low-level modules, and both should depend on abstractions. So what is a high-level module? From your perspective of the application, everything that solves the problem of your application, your business rules, all that is high level of the application. So the reason why you actually write an application, that is the high level module, or are the high level modules of your code. So if your application is about weather, then all the code that you write for your weather handling and all that should not depend on something as low level as the file system or an HTTP client or that sort of stuff. I mean, why should something weathery know about all these technical details? They should maybe know about certain abstract concepts that are data providers that provide you with weather, or formats that get parsed or something like this, but they should not be depending on some very, very specific details of this low-level code. And depending on abstractions also means that if you introduce a dependency, for example, my weather loader component logs some messages somewhere, then it should not be dependent on something very specific like a file logger. Or in our case, as we've seen before, the Google service that depended on an HTTP client. I mean, why should the dependency be on HTTP client when it could be any transport that we can use there? The second part of the dependency inversion principle is about abstractions and concrete implementations. So you always, in object-oriented code, have abstract interfaces or abstract base classes, which only define some public API of something. And you have very concrete implementations of these interfaces. And the dependency inversion principle says that if you have something abstract, so you write an interface, then this interface should not have type hints or dependencies to concrete implementations of other concepts. So if I have a weather service interface, then it should not accept like file logger arguments, for example. This doesn't make sense. I have an abstraction, and this abstraction directly has a dependency to something very concrete. And so I actually broke down the abstraction already. It's not really abstract anymore, it's very concrete. And details should only depend on abstractions if possible. So if I implement something in detail, then all the dependencies of this detail should only have dependencies to abstract concepts. This is very strict, the way the dependency inversion principle is formulated, because it would essentially mean that everything that you implement also has an interface. But this puts very much work on us as developers to do it this way. And it's also very complicated to get this work if you're using frameworks, for example, that already have very concrete implementations of stuff. So it's not possible to apply this all the time to all of our code. But we can apply this to the code that we care most about. So this high-level module we have in our application, where our boss actually wants us to write this, or we make the money with this. This is the important part of code, where we have to think about, does it make sense to introduce dependencies to something specific as, like an HTTP client, in my highly valuable business logic here? Or do I introduce the risk that tomorrow we have changes and we need to rewrite all the code because I didn't implement some abstraction layer here? So in this case, the issue is very specific about, I have this weather loader component, so the biggest class in our system, where we write this the component to fetch the weather. So this is the most important class. It's the big interface in front of this component, and it gets a file logger and a Google Weather Service as dependency. So we have something very generic in a way, that we wanted to write this reusable, and we wanted to allow different strategies, and we implemented in a way where it's very specific to the current implementation. So the file logger, and this for example, has a method here to write to file. So we have this big weather loader component, and we care about details suddenly in this component, and low-level details such as writing to some file, instead of just defining some generic way to log something. So when we write solid object-oriented code and want to not violate the dependency inversion principle, then we have to reformulate our code in abstractions. So I have this detail, this weather loader component, and instead of depending on Google Weather Service and a file logger, instead I rely on abstractions like a simple logger interface and a weather service interface. And by doing this, I am allowed in the future to change the actual concrete implementations of the logger. Logging could, for example, go to Greylog in the future, which is a cool logging service. And Google might change, and I need to change to a different weather provider. So by not violating the dependency inversion principle, I am allowed, it's possible for me to change the implementations of all the concrete classes that I have in the future. And of course I could do this when I write my application and just change all the code everywhere. But the nice thing about this is that I don't have to change everything, but I only have to change the concrete implementations of something. And I don't have to go in all the different cases where this is used and change the code there as well. So I reduce the risk again of having to make too many changes to my whole application and only exchange some abstract concept with a new concept. If we want to write object-oriented software that has nice abstractions from the low-level details, then we should use interfaces and abstract classes for this to allow us to make this changes from very concrete implementation details to something which is not so concrete anymore and allows us to change this in the future. And low-level modules here are not something like just the file logger or the database, but also framework-specific code, for example. So many frameworks, for example, allow me to send messages to the user on the next page by using a mechanism called flash messages, where the messages are written to the session and then grabbed on the next request and shown to the user, for example. And this is already a very, very specific implementation of how this works. So in modern websites that are more Web 2.0 based or sort of like single page applications, we see this more often that the messages that are sent back to the user are actually asynchronous. So somewhere in the code the message is triggered, and this is then sent back, for example, through WebSockets or something to the user, and he sees this at some point. For example, Google Plus works this way, where we always see new messages pop up. And if we depend on something the framework provides very specifically, like flash messages or all the different other APIs that frameworks provide for us, then if we don't have abstractions for this, then this always means when something changes or when we want to change the way our application works, then we need to change all the occurrences that we have there. And this can mean going through thousands of lines of code that use this mechanism to change it. And if we had a simple abstraction that wrapped this, then it would allow us to change this in just a single spot. And the whole application would pick up the new mechanism of sending messages back to the user. So high level here means your code, and low level sort of means the system code or the framework code, or sort of that. One point that is very interesting to see is also which helps make the code much smaller. So procedural code always has the problem that it's implemented top-down, so you're thinking about the use case and you implement all the code that you need to get the use case done. This leads to code handling use cases that can have like 20 lines of code in the first implementation, 50 in the next, and then you get to 100, 200, 300 lines of code for the method that handles the use case. And if you're using object-oriented ways and use interfaces for concepts, then this allows you to think about this in the usage point of view. So you write an interface, for example, for the way you want to use the database, and you might have a very, very specific and simple way how to use the database. For example, get an array from the request and insert it to the database. And then you write a simple interface having this method, insert this data into the database, and it looks very simple for you, and you want to use it this way because it's very simple to you. And it allows you to hide all the implementation details, like how's this SQL constructed, and maybe you need escaping and all this stuff, which might again be 30, 40 lines of code or something, or depending on the way you do it. But it allows, so you can hide all these details behind the simple interfaces that you can come up with. So you think about, okay, I need this now. This is your use case for your new class that you want to invent. And by doing it this way, you actually have control about making it as simple as possible. You know how you want to use it, and you can make it as simple as possible. And this normally leads to code which is very, very small, because you can hide all these details somewhere else in other classes. And this sort of has an effect going deeper and deeper and deeper into more technical detail, but it allows you to have very small code on the high level of your modules. So in your controller, for example, or in the classes that handle your use cases, you might actually be able to read the business rules out there and delegate all the technical details to other classes and be very easy to read this code. And this is something that the dependency inversion principle helps a lot with, if you think about interfaces from the usage point of view. Again, here, finding abstractions is not easy. So you can, of course, start to think about what is a generic way to save things in the database. And then you can waste 10 years of time to implement this. So it's not easy to find these abstractions in your code and define them, but you should still start with something. So think about it as simple as possible. I want to use this in this and that way, and define a simple interface. And you can always iterate on that and make it better or change it. If you're not maintaining an open source project, it's often very easy to change stuff instead of like having to keep it this way all the time. Dependency inversion leads to a new concept called dependency injection, and then a concept also called dependency injection containers. So when you're doing object-oriented code, then dependency injection is what you want at the end. You always want to be able to stuff all the code together in different ways, in new ways. And we've seen this in the code examples, many classes which get their dependencies in the constructor. This is what dependency injection is about. You have one class and it explicitly gets dependencies in the constructor. And this way I'm actually able to change the implementations at runtime. Put in new classes for an interface, change how it works, maybe even have different actual instantiations of this weather service with different providers. So I might change my weather loader component to display the weather for some specific town using different backend services. And maybe Google says me it's 16 degrees and another service says to me it's 15 degrees. So by using dependency injection and injecting the dependencies in the constructor of my class, I'm able to change the implementations as I want. The last principle is called interface segregation principle. So I've talked about interfaces and abstractions and how it's very hard to find abstractions in your code and implement them. And the interface segregation principle sort of puts a point there when you start defining abstractions. And it says that you should not force somebody to use an interface which has lots of methods that he doesn't need. So if you have interfaces in your code which require an implementation to implement 20, 30, 40 methods, then it's very hard to actually do this for different implementations. For example, if you have an interface for something like the database, and you come up with thousands of methods about finding stuff in different ways using SQL and whatnot, then you're making it very hard to implement a different, to build a different implementation of this interface, because it has so many different methods that all have their own assumptions. By adding a new method to an interface, you make it harder for anybody to find an actual concrete implementation that can implement all these methods. So interface segregation says keep interfaces as small as possible and don't make them too big. So this goes to the usage point of view again. Write interfaces in a way where it's very easy to use them and don't make them too complicated. In this case, for example, I have an interface which has two methods, one to get the weather for location and the other one to get a forecast for, of the weather, for example, for the next day or the next 7 days or something. By doing this, I actually prevent an implementation for this for a data service that doesn't have forecast data. So maybe some provider only has the current weather data, not the forecast data. So what do I have to do to implement this method for somebody who doesn't have forecast data? I have to throw an exception there and say, I don't have forecast data or something like this. So I actually break sort of this class because it doesn't work for this specific case. So it's also something that the Liskov substitution principle wouldn't want. I'm sort of making it hard for somebody to implement this. Maybe he cannot implement one of these methods of the interface. And instead, I should split up the interfaces into the specific concerns. So instead of having one which rules it all, sort of, I try to extract the different concerns that they actually handle and have specific interfaces for them. And by doing this, I'm actually able to have much more implementations. Okay, so we have this interface now for weather providers, which only has the getWeatherForLocation method. And now in our code, we say when I only need the current weather, then I have a type hint for this interface, which only requires this one method. So I intentionally make the interface of this class much, much smaller to allow many more implementations. And in this case, it might not be a really good example. One example that we have, for example, in Doctrine, is we have a simple interface for caches, where you set a value and get a value from a cache. And this is essentially it. And at some point, the interface was much bigger. And somebody thought that it would be nice to allow to delete keys based on regex values or on tags or something like this. So you say, every cache key here is a specific tag, and then I want to purge all the cache keys with this tag. And it is possible to implement this for something like APC and memcache and all, but you have to put in lots of work to do this. And then you also maybe have to misuse these implementations to make it possible. For example, in Doctrine 1.2, I think, we added this, and memcache was implemented in a way where for each tag that you wanted to purge, there was a specific key which holds all the keys of the other values that we might have to purge. And then there was one central key which holded much more stuff. So whenever you accessed any cache key, it always also had to access this one other cache key and maybe change this as well. And since memcache is not transactional, we had lots of lost updates there because you read the value there, some other process writes it in the time, and then the next process writes back some illegal values there. So by actually making the interface much bigger, we introduced lots of problems for implementations because they had to implement them in a very bad way. And this made it very hard for users to use this cache because it was not usable anymore. It was really broken. And by having this small interface just with get and set, it allows us to implement thousands of different cache providers which don't have transactions and which are very simple. And we don't have to make compromises about how we do these implementations. It's so simple that everybody can do it.
Sorry.
Yeah.
I have a question.
Yeah.
What if, let's say that you're starting something, and at that moment that you're starting an interface, it makes absolute sense to do something that because the data that you have at that moment, you can say, okay, I can create this method, and all the data will, I don't know, all the other classes that will use the interface will be able to handle that.
Yeah.
Because that's the data that you have at that moment. Then you get new data with time. How do you solve that? Because you already designed an interface that at that time was totally perfect for what you needed. But now something new came up, and you need to modify that interface because the new data that you have or whatever doesn't implement that.
Yeah. First, by thinking about, so the question was, when you start implementing an interface for something, then you obviously have the current use case assumptions in mind, and you might define the interface in this way. And if the future changes these assumptions, then you might need to change the interface. And the question was, how do you prevent having to do this? So first, you have to think in terms of like abstractions and details. You have to, when you write an interface, maybe think about like how can I formulate this in an abstract way. But you obviously also want to prevent over-engineering, and you want to be very specific because you know you need it this way, you want to use it this way. So there, the question is, when the data just changes for this one use case and you have 100 other use cases, maybe just introduce a new interface that allows you to do this in the new use case. But when all the cases change, then you obviously have a reason to change the interface. So in terms of like the open-close principle said, don't change all the stuff all the time. So when one of the use cases where you use something changes, then try to find something new for this use case. Don't change it everywhere else as well. Yeah. This obviously leads to lots of classes in your code. Yeah? So everything I've shown here always sort of meant introducing more classes, introducing more interfaces. So I personally only apply this in very strict detail to code which is very important and of high business value. So whenever the business value declines or is not so important anymore, I tend to loosen this constraints much more, because then it doesn't make sense to prevent all these possible changes because the business value is not there anyways. Okay, so summing up the interface segregation principle, try to avoid injecting dependencies that do too much. So try to keep it only in a way that classes get access to the values that, or access to interfaces that they actually need. This is something that frameworks consistently do wrong. For obvious reasons, a framework has to cater to 80% of the use cases, or maybe even trying more. And this lets them write interfaces for you to use that are way too big. So the normal controller API that you get from any framework, Symfony, Zen Framework, HTTP or something, allows you to access all the functionality that the framework has in some way. Either by going somewhere global and getting into something there, or by having some sort of object which knows about all the other objects. So you have tons of possibilities to get at all the different functionalities. And by being able to do that, you will actually write code that does it. So being allowed by the framework to access everything, why not do it and access everything? So you create something which depends on many, many different things. And by that becomes very explicit and very hard to change. And this is something that the interface segregation principle tries to prevent. So this have been the 5 solid principles, and if you haven't seen it by now, they all started by the letters, so they sort of like define the solid abbreviation. And from my perspective, the single responsibility principle and the dependency inversion principle are actually the most important ones. And the single responsibility principle is also very easy to apply day to day by thinking about, is my code written in a way where it does way too much, and I sort of want to start splitting out the code in different components that handle their use cases more properly and more specific. And the dependency inversion principle prevents me from using, very nice. The dependency inversion principle prevents me from writing code that depends on very concrete abstractions, very concrete code like SQL statements, for example, framework code and all that. So it allows me to write my code in a way which is a little bit more abstract from all the technical details that we use day to day. Okay, so are there any questions? Yes?